Okay, kind of like we were talking about with microscopes, they very often will use very low, high frequency wavelengths such as blue light because rather than diffracting around and missing the object, it will reflect it back and you can see that light. The extreme of that would be electron microscopes, which don't even use light wavelengths, but actually electron waves. And electron waves of electrons act somewhat like a wave as well as a particle. And they are about 100,000 times shorter than light, so we can look at extremely small things with those. Okay, and so now another example of this idea is the idea of diffraction grating. Diffraction grating is basically a piece of looks almost clear, but actually, if you look at it microscopically, you can see it has little slits on it, and these little slits cause the light rays to bend around them. And when they do that, it also separates out the different wavelengths of light. And so as they bend around that, you can see the different colors of light. And sometimes you'll hold these up and we'll do some in class, and you can see the rainbow colors around everything. You may have some glasses like this you can put on, and you see rainbow colors everywhere you look at the light. Now, when studying diffraction of light, they would shoot one color of light through, or one color, so that then it wouldn't, the light would go through slits and diffract, so it would give you all different wavelengths like we talked about in the diffraction grating. So if you do just one color of light, so that way you don't have to worry about that part of things, they noticed that you had this interference pattern. What they would say is, okay, here's the light coming from here. If the light ray from this slot and light which was coming from this slot, if they're both going up at the same time and down at the same time, then they reinforce each other, and you have these really bright bands. Okay? But if those two light rays would hit where they cancel each other out, then it would cancel each other out and you would get dark, no light at all. And in between you would have kind of lighter and dimmer as it kind of go back and forth. And so you have bright, getting darker, in the middle dark, and then getting brighter light and so forth. And you would have these bands start showing up where they either interfered with each other or where they either cancel each other out or they actually land on top of each other. Now, which they do depends, like we showed, just upon how they line up with each other. If they're both going up at the same time, down going at the same time, that would be a positive type of interference. The two waves interfere with each other, but since they're both in sync with each other or in step, then they're reinforcing each other, and you get a brighter light. Okay? If they're completely out of step, where one's going up and the other's going down, they completely cancel each other out, and that's what you're getting in these dark spots. Okay? Now, it could be that, for example, this one's part of this, the up, is canceling this one, but then the down part is not as strong, okay, for example, this one, and they're not quite lining up, so you get what we call partial cancellation. They might dim the light, okay? And this is due to interference, okay? And so interference is anytime they overlap, they can be constructive interference if they're all lined up together, like the ones we talked about here. If they're all going up and down at the same time, it would make it brighter. If they're opposite of each other, out of sync, or out of step with each other, then they cause dark places, okay? And so just like we talked about with sound and some other ways, you can have the same kind of interference. Another common example where you might see this interference pattern is on a swimming pool or a bathtub for that matter too. But when you have waves going across the top, okay, basically that's causing the waves to bend. In some places you're getting more concentrated light. Other areas aren't getting light rays bent toward them, so they're darker. And so you can see this kind of pattern where the brighter areas are where waves are light waves are being bent so that they all hit the same place, and you have positive interference. The darker parts in the middle, of course, is where you're having the destructive interference or cancellation, so it's darker spots in the water. Now, another characteristic of light is that you can polarize light. And what does that mean to polarize light? Well, let's look at it this way. We said that we have a transverse wave. Light is a transverse wave going up and down, up and down, up and down. But it could also be side to side or some angle in between that. And so it's just going perpendicular to the direction it's going. If it's going this direction, then it's going to be going perpendicular to that. But there's a whole, it can be rotated around that axis. Okay? And polarized filters, which are, we probably most commonly hear about polarized sunglasses, help block light rays that are we say they take the glare off. Well, what we really mean is usually when light waves bounce off of something, the glare are the ones that go horizontal, usually more like these waves over here. They're going more horizontal. Those are the ones that cause most of the glare. So what a polarized sunglasses is, it's kind of like a picket fence. And it has slits that allow things to go up and down. So any of the light rays that are going up and down can come through. But if you put it through one where you turn one this way and one this way, then it will block out all the light. Okay, so polarized sunglasses would be like this. They're up and down. They allow only the light that's coming up and down to come through, so you still see light, but it blocks all the side-to-side rays. If you had one trying to go like this, it's not going to make it because it's going to get cut out of there. It's going to get blocked. And so most of what we call glare are light rays that are going more horizontally, and they would be blocked out by this light. Okay, now if you take two polarized filters and you put them up and down, you get about the same thing coming through. All right, and we'll look at this in lab, but let me get you an example down here just to show you what it would look kind of like. Maybe not. All right. Okay. And it may not look as good as I was hoping, but let's try it. Okay, here we go. On a polarized filter, if you have both of them straight up and down, then you can see that most light comes through, and this part look almost the same looking through two filters. But now when we rotate one of them, top one has been rotated 90 degrees, now you've got almost right here a totally black area where no light's getting through. All right. But interestingly enough, if you put a third filter between those two filters that are turned opposite directions, and you rotate it at 45 degrees, it will let light through. Now, that's a little beyond what we're going to discuss here, so I'm not going to worry about that. I just want you to understand the first part. If they're both going the same direction, then they're going to let light through. But if they're turned opposite directions and you're blocking light going up and down, and you're blocking light going horizontal, you pretty much block all the light out. Why does the third one work? That would be a good research thing for someone to look up. Now, sometimes we talk about light, we talk about light rays. Sometimes we talk about light as a ray or a wave. And basically, that's kind of the same thing that we're talking about there. But sometimes light can act like a particle, and this is called the wave-particle duality of particles. And it's kind of hard to explain. That sometimes it seems to act like one and sometimes it acts like the other. Most of the things we've been talking about, like polarizing, was obviously a good sign of how things acted as transverse waves, and it could be blocked if you turned the picket fence of the polarized filter one direction, then it would block them out. And that made really good sense for that. But another phenomenon that Einstein and some other people came into is the idea of photoelectric effect. And we are familiar with that, even though we may not call it that, if you've had a solar calculator or solar run anything. And basically what they found out is that when high frequency light hits an object, it knocks electrons loose, okay, or ejects electrons. Now, if those are all ejected in the same direction, you could get a flow of electricity. And so all of solar energy depends on this, the idea that you can take high frequency light, hit certain types of metal, all right, and it will knock loose electrons and cause an electron flow. And the electron flow is a current, and therefore that electricity can be used for things. And this is the whole idea between all our solar energy and solar panels and all this sort of thing. It turns out that it's actually the frequency of the light, and it has to be violet or UV light to be high enough frequency. Okay, how bright the light is does not really affect it necessarily. Okay, or the amount of energy in the light, or the amount of light. It is the right frequency. All right, and so if you're trying to do it under a light bulb that still has UV or violet light, it will still work. But sometimes if you're in a light bulb that only has lower reddish, yellow colors, it may not work because they may not have the high frequency light that you need to keep your calculator or whatever going. I had a calculator in the car that was kind of like that. It usually wouldn't work under just regular light, so I finally got rid of it. All right, but in this case, light acts like there's little particles hitting and knocking loose electrons. And so we say that These are, when light behaves like a particle, we call those particles photons, and you may hear about photons. Some radiation and cancer stuff, proton, but there's also photon radiation that they will use. But basically, photons have to do with light acting like a particle. Sometimes light acts like a wave, and so this is called the duality of matter, or the wave-particle duality of matter. And it just says that sometimes light acts like both ones. Which is it? Well, probably both. Whatever, our job is basically whatever will explain it, then we'll go with that. The last thing we'll talk about are lasers. How do lasers work? And a laser, basically you have a flash tube up here, and it gives off light or energy. As it does that, it excites these atoms that are in here. Okay, and they may be hydrogen atoms. Sometimes there's helium. There's different type of lasers, but helium is one of the very common ones. And it excites these atoms. Once these atoms are excited, then they begin to give off, emit light. Okay, now the light goes off kind of in all directions. Okay, notice that at each end you have these mirrored or partially mirrored surfaces. Okay, and so the light begins to bounce back and forth through the tube. Now at the end, there is a slit that will only allow certain light waves to come out. Okay, and these come out, and they come in a very concentrated, strong beam. A beam that can sometimes be used, for example, to light a match head. We've had some lasers that you can actually light a match using them sometimes. Sometimes not, depending, but it's strong enough to do that. It's very strong, concentrated light. So, well, what makes a laser work so well? Why can you point a laser and see it on an opposite wall or something like that? Okay, well, basically, the light rays that come out, first of all, are monochromatic, meaning only one color. Okay, a lot of helium lasers, I believe, for example, are usually red, but there's blue lasers in different colors depending on what gas that they have in there. Okay, and so they're monochromatic, so they're all the same color, therefore they're all the same frequency. So that means they're the same color, but they are also the same frequency. They are also what we call coherent. In other words, every one of them is in phase, okay, or in step with each other. Okay, so when one goes up, the other one's also going up, and so forth. Okay, so they are in phase with each other, which we know concentrates them, kind of like when you have positive interference, sort of like that. And they are also collimated. Collimated, that's not a word we use, but basically they're all parallel, going side by side in the same direction, same complete parallel direction. Everything is lined up completely about them, not just going up and down, but everything. They're all side by side going the same way. And so because of this, you have a very strong beam of light that can be projected long distances. As it gets farther and farther away, depending on how good the laser is, they can start to spread out a little bit and separate, but much, much stronger than you would expect, so the flashlight or any other kind of light source. And so that's basically what lasers do. Now, lasers can be used to cut things, surgeries. A lot of surgeries are done with lasers, and so forth. A lot of industry that does cutting and so forth with lasers. Light. If you give a presentation talk, a pointer, puts a little dot on there, that is also lasers. Besides playing with cats and driving them crazy. Lots of good purposes that come with lasers, but that's basically what they do. They basically are light that has been monochromatic, it's all the same frequency, it's coherent, which means it's in phase or in step, and collimated, which means it's all parallel, they're all going exactly the same direction at the same time. Everything is coordinated. Kind of light that has it all together, if you will. And that basically brings us to the end of our lectures on light. I know it breaks everyone's heart, but there it is. We'll see you, and that's basically it for this semester. I'm going to say, hopefully, maybe some of you will see you in the second semester.